So let's look at the implementation. It's in the module even odd. And if you're wondering about that name, it's just because if the sum of the two choices of the two numbers that the players pick is even, then the first player wins, and if it's odd, the second player wins. Which is the same as what I said earlier, that if they agree, the first player wins, and if they are different, the second player wins. And I called the first and second player first and second instead of Alice and Bob here. So the data type game is used as a parameter for the contract. So G first and G second are the two players identified by their public key hashes. G stake is an integer that denotes the number of loveless that are to be used as stake in the game by each player. And then there are two deadlines, play deadline and reveal deadline. So play deadline is by what time the second player has to make a move before the first player can claim back his stake. And the reveal deadline is in the case that the second player has made a move, how much time the first player has to claim victory by revealing his nonce. Now the last field in this record type, the G token of type asset class, needs some more explanation. This is an important and common technique that is used in contexts like this. So often we have a situation where we have state in some form. So in our case, it's the game. And as I showed you in this diagram just now, there are a couple of states. So after the first player opens, the state would be the hash of the nonce concatenated with the choice of the first player. And then if the second player replies, the state would be extended by also including the choice of the second player. So on a blockchain like Ethereum, where we have mutable state in the contracts, we would model it just like that. So we would simply update the state of the contract in place. However, in Cardano, everything is immutable. So nothing can ever change. UTXOs are either unspent or they get spent by a transaction and new UTXOs get created. But we never are able to change an existing UTXO. Once it's there, it's immutable and will always be the same until it's spent. However, that doesn't mean that we can't do things like this game where we have changing state. We just use a technique that's also very frequently used in Haskell, for example, that instead of changing state in place, we simply create new state. So in the case of the Cardano blockchain, that means we spend the UTXO and create a new UTXO, which then contains the extended datum or the change datum. However, this causes a problem because how do we know that this new UTXO corresponds to the old one? We somehow must link the two together so that there's like an identity or continuity between the two, so that one can see that the old one and the new one belong together and that they represent a state change. Actually, we saw this already in the very first example I gave you in week 1 with the auction, but then I didn't elaborate and didn't explain so much about it. So the idea is, the trick is to use an NFT for this. So we put an NFT into this UTXO, so add it to the value. I mean, there can be other value in the UTXO. In the case of this game example, the stake that the players put in. But in addition to that, we have this NFT. So when the first player opens and creates the UTXO, the first player also has to add this NFT to the value. And then when the state changes, so in our example, that happens when Bob makes his choice, Bob will create a transaction that consumes the existing UTXO and then creates a new one with the updated datum, still containing the same NFT. And this is exactly what links these two UTXOs together, the NFT. So in order to find the current state of the game, we must just look for UTXO at the correct address, the address given by the validator script for the game, containing this NFT. And then we know we have found the right instance of the game. the right UTXO. And that's why I need this last field here, the token. So that will be the asset class of the NFT that we use to identify the correct UTXO. So sometimes that's also called a stake token if an NFT is used for this reason. There's an additional reason, maybe even more important than just linking old and new state together, namely that on Cardano, validation only happens when an UTXO is spent. So the validator script only runs when somebody tries to spend an output sitting at a script address, but not when you produce an output sitting at a script address. Which means in the case of this game, anybody could create a UTXO with exactly the same datum as the first player does. So there is no way to prevent somebody from trying to disturb the game or trying to disrupt the game by creating one or more UTXOs at the same address with exactly the same datum. So how do we know which one is the right one, the real one, the one created by the first player? Or how do we force the first player to only create one UTXO, not several? And that's the reason why we use an NFT for this state token and not some arbitrary native token. Because an NFT by definition is unique and only exists once. So anybody can produce a UTXO that contains this datum, but only one of these UTXOs can actually contain the NFT as part of its value, because the NFT only exists once. So there can be at most one UTXO sitting at the address with the correct datum and containing the NFT that corresponds to the G token field given as part of the datum. So that's an important technique, as I said, and that's used all the time to make things unique and to point to the one and only instance of a contract, for example, that we are interested in. Then the type game choice. So that's just the two moves the players can make, 0 or 1. And I derived equality in the normal Haskell sense and an odd instance, but unfortunately for the Plutus equivalence of eq and odd, that's not possible. And I need eq for Plutus eq, so I do that by hand in the usual way. So, 0 equals 0 and 1 equals 1, and all other combinations are not equal. And for this to work with template Haskell, you have to put this inlineable pragma there as well for the equals operation. And game datum is what I will use as state for the contract. And byte string is the hash that the first player submits. And maybe game choice is the move by the second player. It's a maybe because in the beginning, the second player hasn't yet moved. So then it will be nothing, and once the second player has moved, it will be a just. And same thing, I also need Plutus equality for game datum. And just also the obvious one that 2 are equal if both components, the hash and the maybe game choice, are equal. Now we come to the redeemer, and for that I also implemented a custom type that I call game redeemer. And that corresponds to the transitions we saw in the diagram I drew just now. So play is when the second player moves, and as argument it has a game choice. So the second player can play 0 or 1. So that will be play 0 or play 1. Reveal is for the case when the first player has won and must prove that by revealing its nonce. So the byte string argument here will be the nonce. We don't need to also provide the move that the first player made, because he will only reveal in the case he has won, and we know what move makes him win. So that would be redundant, and therefore I left it. And finally, claim first and claim second. Claim first is in the case when the second player doesn't make a move, so the first player can claim back his stake. And claim second is for the case that the first player doesn't reveal because he knows he has lost, so the second player can get his winnings. Then I have two helper functions. one I call it Lovelaces, which given a value extracts the amount of Lovelaces contained in that value. Last time I checked, there wasn't a function like this in the library, but maybe it has been added in the meantime or I just didn't see it. But in any case, it's simple. There's a function from value that, given the value, extracts the ADA, but that is not an integer, it's a new type wrapper around the integer. So I get to the underlying integer with this getLoveless function. And the second one, given a maybe datum, tries to deserialize that if it's a just to a maybe game datum. So I write this in the maybe monad, which means this first step here, that if the argument, the MD, is already nothing, I will return nothing. And if it's just datum D, then I try to deserialize that into a game datum. Now we come to the core business logic in the make game validator function. The first argument here is the parameter of the game type that I just explained. The second and the third argument are somewhat of a nuisance, and I just need them due to the fact that, as we have already discussed on Discord, it's not possible to use string literals to get byte strings in Haskell that is compiled to Plutus core. And I want string literals representing the 0 choice and the 1 choice. So this will just be the byte string with the digit 0 and the byte string with the digit 1. But because I can't use string literals, I pass them in as auxiliary arguments. We'll see how we pass them in later. Then the usual datum, redeemer, and context. Before we look at this main logic here, let's first look at a couple of helper functions. So info just extracts the tx info from the context. Own input uses a function find own input. We can look at the documentation and we see it takes as argument a script context and then returns a maybe tx info. Find the input currently being validated. So why a maybe? Well, because scripts are not only for validating inputs, but could also used, for example, for minting. So in the minting case, we would get nothing here. But in the validation case, we get a tx in info, and a tx in info is a record type with two fields. One is the tx out ref, the reference to that input, to the output we're trying to consume, to spend. And the other one, tx in info resolved, is the actual output. And it's the actual output I'm interested in here. Therefore, in the code, I first check whether I get nothing. So that would be the case if I'm not validating. So I trace an error. And if I'm validating, I get this tx in info, and then I extract the tx out from that. Next, own output. So as I explained before, the idea is that during these state transitions, we always consume the current game UTXO and immediately produce a new one at the same address with an updated datum and possibly an updated value. And there's a function for that as well that helps there, get continuing outputs. So given a script context, it returns a list of tx outs of outputs, and those are the outputs that sit at the script address I'm currently validating. So here, as in the documentation, finds all the outputs that pay to the same script address that we are currently spending from, if any. So again, if we, for example, in the minting case, this would be the empty list, but also if we are validating, not all transactions create a new UTXO at the same address. But if they do, then all the outputs at the same address are in this list. And in our case, I expect there to be exactly one such output. So not 0, there must be one, but also not more than one. So I just pattern match against the list that I get as a result, and if that contains exactly one element, that's the output I'm interested in, and otherwise I trace an error. Next is the function output datum. The idea is that that should give me the datum of type game datum of my own output. So the one output that goes to the same address again. And for that I'm using this helper function game datum that I showed you earlier. Recall that takes a maybe datum and then returns a maybe game datum. So where do I get my maybe datum from? Well, first, this txout type has a field named txout datum hash. So given my own output, I now have the datum hash of that output. Now, as I explained many times before, the producer of a UTXO is only required to include the datum hash, not the datum itself, but can optionally do so. And in this case, we do rely on the fact that the producer of the transaction, producer of the UTXO, actually does so. So we insist that the datum is actually included. And there's a function find datum. We can look at the documentation. So find datum takes a datum hash and a txinfo and then returns maybe a datum. So if the datum is included in the transaction, it will return the datum corresponding to the given datum hash. And if not, then it will return nothing. So I have to use flip here. Flip is a standard Haskell function that switches the two arguments of a two-argument function. So we saw that info was actually the second argument, but by using flip I make it the first. So then the second one is the datum hash, which I feed in here. So this bind is actually the bind in the maybe monad. Because this step can fail, it could not have a hash attached. So this is only optional that outputs or UTXOs have datum attached. So this could fail, and then this lookup could also fail. But if all goes well, I get a maybe datum, and then I use my helper function to turn that into a game datum. And all of this can fail, but if it does, I trace an error, and otherwise I return this game datum. So check nonce is for the case that the first player has won and wants to prove it by revealing his nonce and then proving that the hash he submitted in the beginning of the game fits this nonce. So the first argument is the hash he submitted. The second argument is the nonce he now reveals. The third argument is the move that both players made. It's called cSecond here, move of the second player. But this function will only be involved or only be relevant in the case where the first player knows he has won, which is only the case when he made the same choice that the second player made. So I could just as well have called it C first in principle. And in order to do this check, I mean, how did the computation of the hash work? Well, I take the nonce and concatenate it with the choice. But the choice, of course, here is of some abstract data type game choice. But in order to concatenate with the nonce, I need it in byte string form. And the idea is I just use this B as 0 for the 0 choice and B as 1 for the 1 choice. So this is just this conversion. And I call the byte string C first. So C second is of type game choice, but C first is of type byte string. And if the choice was 0, I take the byte string representing 0. If it was 1, I take the byte string representing 1. Then to compute the hash, I take the nonce, concatenate it with this byte string, and apply the SHA-256 hash function to it. So this is the hash that I get giving this nonce, and then the check is to make sure that that is indeed the hash the first player committed in the first place. And finally, I haven't mentioned that before, but we now have this state token, this NFT that identifies the correct UTXO. And the question is what happens to this NFT after the game is over and there is no UTXO at the game address anymore. And the way I've implemented now, I wanted to go back to the first player. The first player needs to have it in the beginning in order to kick off the game and put the NFT into the correct UTXO. So I think it's only reasonable to give it back to him in the end, no matter who won the game. So this just checks, there's a function called value paid to and gets the context or the info from the context and pub key hash, and then it basically adds up all the values that go to that pub key hash in some output of the transaction. So I want that, so this just means that the first player gets the token. Actually, one has to be a bit careful here, but for simplicity, I left it like this. So this value paid to only looks at the payment part. So it considers all outputs where the payment part of the address belongs to the specified hash, so in our case to the first player. But recall that an address has two parts, a payment part and a staking part. So normally, if you work with a Daedalus wallet, for example, and you stake to a pool, then automatically things will be set up in a way that the staking part of each address that you use makes sure that you receive the rewards. So the rewards go to your own wallet. However, that's not necessarily the case. So you can have addresses where the payment part belongs to you. So you can decide if and when you want to spend the UTXO, but the staking part could benefit somebody else. So the staking rewards incurred by the UTXO could be paid to somebody else. So a malicious player could, in this step here, indeed pay back the NFT to you, but use an address where the payment part belongs to you, but the staking rewards go to himself. Now, of course, in the case of an NFT, there are no staking rewards, because staking rewards are, at least for the time being, only paid for ADA. However, of course, the same is true, for example, the winnings of the game. So one of the player wins, and we will make sure that the winnings go to the winner. But there, this could also happen, that the loser basically does pay the winnings to the winner, but uses an address where the payment part belongs to the winner, but the staking part belongs to himself. So he would indeed pay the winner the win, but as long as the winner leaves it at this address, he himself, the loser, would still receive the staking rewards for this. So as I said, I haven't fixed it in this example. I mean, it's just an example anyway, and I wanted to keep it simple. And I mean, this is a silly game, so probably the stake is only 1 ADA or something. So the staking rewards are negligible. However, I want to point that out, that you have to be careful about this. You always have to keep in mind that payment component of an address is not the only component. So there is a staking component, and it's not guaranteed that that benefits the same user that the payment part belongs to. Actually, there have been cases in projects building on Cardano, commercial projects, where this wasn't taken into consideration. So that's a potential security hole. I mean, the payment part is still correct, so nobody loses funds over this. But of course, depending on the application, the rewards can also be quite significant. So again, for this example, I have ignored this, but I do want to point it out that for a real application, especially if it's about a lot of money, you have to be careful about that. So probably to do it correctly, I should have added more fields to the game type and not only recorded the hashes of the first and the second player, but also addresses for them, so that the players can determine an address where they want their winnings to go to. And then, of course, they could pick an address where the staking component actually also benefits themselves. But to keep it simple, I didn't do it in this example. So now we can look at the conditions. There is one condition that applies to all cases simultaneously, and that is that the input I'm validating must be identified by the state token. So that's what I'm checking here, that the own input, the input I'm presently validating, contains the state token. And then what the rules after that depend on the situation I'm in. The first situation is the one where the first player has moved, the second player is moving now. So this is the transaction where the second player moves and chooses the move C. So the datum, the second component, must be nothing. Remember, that just means that the second player hasn't moved, so is moving now. And in this case, what do I have to check? I have to check that this move is indeed made by the second player, so he has to sign the transaction. This checks that the first player has put down the stake for the game. Then this checks that now in this transaction the second player adds his own stake. So in the output we now have twice the G stake game. Then we know exactly what the datum of the output must be. It must be the same hash as before, but now the nothing is replaced by just C, where C is exactly the move the second player is making. Then the move has to happen before the first deadline. That's exactly the point of this first deadline, the play deadline. Until then, the move must have happened. And finally, the NFT must be passed on to the new UTXO to identify that again. Okay, the second situation is both players have moved and the first player discovers that he has won. So in order to prove that and get the winnings, he has to reveal his nonce. So in that case, it has to be signed by the first player. The nonce must indeed agree with the hash he submitted earlier. He must do this before the reveal deadline. The input must contain the stake of both players. And finally, what I just said, the NFT must go back to the first player. First case is second player hasn't moved yet and also doesn't move in the deadline, so the first player wants his stake back. So this must be signed by the first player. It must only happen after the deadline has passed. The first player has provided his stake and he must get the NFT back. And the last case is both players have moved, but the first player has realized that he didn't win and therefore didn't reveal his nonce, or he got disconnected or whatever. In any case, he missed the deadline. So in that case, the second player wins, but the second player must sign this transaction. So it must not happen before the deadline. He can only do that once the reveal deadline has passed to give the first player enough time to reveal the nonce if the first player won. We check again that the input, the consumed UTXO, has the correct stake. So in this case, both players must have provided their stake. And even though the second player has won and gets the money, the NFT must go back to the first player. And that's all legitimate transitions we can have. So in all other cases, we don't validate, we fail validation. So now let's look at the rest of the on-chain code. As always, we define this helper type that just bundles the information about what the datum and what the redeemer type are. Here we define the byte strings we're actually going to use for the two choices, 0 and 1. This is completely arbitrary. I could pick any two byte strings there. Typed game validator that compiles the code as before. So it's parameterized now by game and these two byte strings. This make validator function, so I have to apply all of them. But I just use these constants here. So now I only left with this one game parameter, as one would expect. Then the usual boilerplate for validator and address. Now, as preparation for the on-chain code, for the off-chain code, we will always need to find the right UTXO, so the one that carries the NFT. So I write this helper function find game output that gets the game, and then in the contract monad tries to find the UTXO. So it could fail, the UTXO could not be there, so therefore maybe. And then I return the usual things, the reference and the output itself, and additionally the game datum. And that's quite straightforward to implement. So first I get all the UTXOs at the game address. Then I use this find function. This is in data.list. And it's more general. It doesn't only work for lists, it works for more general containers of type T, but you can think lists. So it gets a predicate on elements and a list of A's and returns a maybe A. And the logic is if it finds an element in the list that satisfies the predicate, it will return it as a just, and otherwise it will return nothing. So if we do find even, 1, 3, 5, 8, 11, 12, it will pick the first even number from the list, just 8. But if I remove the even elements, then it will return nothing. So using this find, after we have all the UTXOs, turn them into a list of pairs. Then as F, we take such a pair, ignore the reference, just take the O and check whether this output contains our token. So this line, which by the way happens in the maybe monad, will, if it exists, find us the UTXO that contains the token. And then we use the earlier defined helper function game datum to get the datum to this UTXO and return the triple. Now there's a second helper function, wait until time has passed. The idea is it gets a POSIX time and then it waits until that POSIX time has passed and we are in the next slot. So how do I do that? I get the current slot, I just lock it, then I use something provided by the contract monad called await time, which does what it says. So it gets a POSIX time and waits, blocks the contract until that time has come. And then just to make sure that I'm in the next slot, I wait for one slot using wait end slots. And I just, for information, ask for the now current slot and also lock that. Okay, so now we have two contracts for the two players. One for the first player to play the game, the other one for the second player. The second player plays the game. And with corresponding parameters, first params and second params. So first params, we don't need the first player. The first player will be the owner of the wallet that invokes this contract, but we need the second and the other things we need to define the game, the stake, the two deadlines. Then we need the nonce that the first player wants to use to conceal his choice. And then the NFT, which we split into currency symbol and token name. And finally, the choice, the move that the player wants to make. So in this contract, first get our own public key hash. Then we can define the value of the game type. So we put our own public key hash as first player and then use the parameters we got from the first params. And for the token, we just assemble the currency symbol and token name into an asset class. Then this V value is just our stake that we must put into the UTXO plus the NFT that we must put into the UTXO. C is our choice. Now we compute the hash that we must put there, our commitment to our choice. So we take the nonce and concatenate it with, well, if we want to play 0, this 0 byte string, and otherwise the 1 byte string, and hash the result. The constraints for the transaction are very simple. All we have to do is we must produce a script output at this address with the datum that contains the hash we just computed. Nothing for the second player because obviously the second player hasn't played yet, and the value we computed. And we wait for transaction and lock a message. So now the second player has a chance to move, but it must happen before this play deadline. So what we do now as first player is we wait until this deadline has passed. And then there are several cases. So we check whether we find UTXO containing the NFT. If we don't find it, then something has gone very wrong that can't actually happen because this can't just disappear. We know we just produced the UTXO at this address, and all anybody else, the second player, can do is make a move, but that doesn't destroy the UTXO. I mean, it removes the UTXO but produces a new one at the same address again. So we should find it. There's no way we cannot find it. But nevertheless, if that happens, then I'm throwing an exception. But normally we will find it. So we have this triple determining the UTXO and the datum. And in this case, the second player hasn't moved. So the deadline has passed, the second player hasn't moved. So what we can do is we can invoke this claim first redeemer to get our stake back. So as constraints, we just say we must spend this UTXO we found with this redeemer. And as lookups, we need to provide the UTXO and we must provide the validator of the game. And in that case, we log that we reclaimed the stake. Second case is that the second player did move, and there are then in turn again two cases, that the second player moved and won, or that the second player moved and lost. So this is the case where the second player chose the same move that we played, so we won. And in the other case, the second player won, and we can't do anything, so we just don't do anything. But if we won, we must now reveal our nonce to get the winning. So we use the reveal nonce redeemer, and we must also submit this transaction before the deadline for revealing has passed. And we again need lookups. We again need to specify the UTXO, and we must provide the game validator. And then we submit and wait and have won. Now for the second player, the parameters are very similar, except that now we don't need to provide the second player because that's us, but the first player, stake, and the two deadlines as before, currency symbol and token name for the NFT as before, and the choice, the move we want to make. We don't need a nonce now because the nonce was only for the first player. Okay, so we start by looking up our own public key hash and can then define the game value, similar to as what we did for the first player. And now we try to find the UTXO that contains the NFT. So if we find it, and so BS is the commitment of the first player, the hash, and nothing because we haven't moved yet. So in that case, so we found the game. So this is the most interesting case, but let's look at the second case that it's not like that. Well, in that case, we just didn't find a game where we can move, so we can't do anything. So it's enough to concentrate on this case. So we found the game, and now we want to make our move, so invoke the play redeemer. So token is the NFT. Now V is the value that we must put in the new output. Remember, if we do the play transaction, we must consume the existing UTXO and produce a new one at the same address. And the old one should contain the stake that the first player put in, and now we must add our own stake and we must keep the NFT in there. And the NFT, of course, is also contained in the on the input side already. So what we must put in the output is, so X is just local variable here to, so that's the stake in Loveless. So we must into the output put twice the stake and the NFT. C is our choice. Let's look at the constraints first. So we must spend the existing UTXO with redeemer play, our choice. Then we must create a new UTXO with the updated datum. So same BS, but now just C, just our move. And this V we computed, which now also contains our own stake in addition to the first player's stake and the NFT. And we must do this before the deadline passes to make the play move. And we need lookups, so we must provide the UTXO. And because we are consuming the script output, we need the validator. And because we are producing one, we need the script instance. Then we do the usual thing. So we submit, we wait for confirmation, we log. Now it's the first player's turn again. So we wait until this reveal deadline has passed. And we again try to find the UTXO, which will now or could now be a different one. That's why I call it M prime. So if we don't find an UTXO anymore, that means that in the meantime, while we were waiting, the first player revealed and won. So in that case, we have lost, we can't do anything. If we still do find the UTXO, it means the first player didn't reveal, which means either the first player left the game for whatever reason, or he lost and couldn't reveal. In any case, now we can claim the winning. So we must spend the UTXO we found. We must do this before and after the reveal deadline has passed, because until then the first player still would have time to make his revelation. And we must hand back the NFT to the first player. There's one extra thing we have to take care of here. Namely, we can't just send the naked NFT back to the first player, because there is this min ADA rule that every UTXO has to contain a minimal amount of ADA. So we have to add some ADA to that. So I had to add this here. If you recall, in the last lecture, I used this adjust function to adjust an unbalanced transaction. Here I basically do it by hand. There's this min ADA TX out, which I think is set to 2 ADA. And this is of type ADA. So if I extract the underlying value with get ADA and then use ADA value of, I get a value. So I add that to the token. And that's of course a bit unfair that the second player has to pay this if he wins. So probably one would need to adjust for that and maybe make the first player put down this deposit in the first place when he starts the game. I didn't worry about this now, but just wanted to point it out. So for the lookups, we again need the UTXO and the validator, and then we can submit the transaction and log that the second player won. And that's it. That's the two contracts for the two players. So here I define the schema. So two endpoints, one for the first player, one for the second player, called first and second. And then in the usual way, I assemble the two contracts into one contract that I call endpoints. So as before, I give the choice between first and second, block until one of the choices is made with await promise. It's implemented by just using the contracts we just defined, first game, second game. And then recursively, I call endpoints again. And that's it. That's the complete code. Now let's test this using emulator traces. So I created a module called week 7 test even odd. And the idea is that you can test it for all choices. So here's this test prime function where you can give first player choice and second player choice. And I also have this combine function that just calls test prime for all 4 possible choices. I define the two wallets, W1, W2. I just use these mock wallets, known wallet 1, known wallet 2. And I use this variant of run emulator trace IO where I can specify an initial condition because I want both players to have 1000 ADA and I want the first player to hold the NFT in the beginning. So I just make up a token where I define some arbitrary currency that of course doesn't correspond to a real minting script, but it's just for testing now. And I just give it the token name state token. So the first player, wallet 1, will start with 1000 ADA and this token, and the second player with 1000 ADA. Now I define the trace. As I said, the two parameters are the choices by the first and the second player. So I log this. Then I start the contract endpoints for both wallets, get two different handles, one for the instance of the contract running for wallet 1, the other one for the instance running for wallet 2. I look up the two payment pub key hashes belonging to those wallets. I just use a stake of 100 ADA and I arbitrarily set the deadlines to 5 slots and 10 slots, which of course for a real game would be far too fast. So of course a block only comes on average every 20 seconds. So you must also allow for variation in that. So you should not assume that the block will be there in a minute, let's say. So probably the shortest deadline that would make any sense would be something like 2 minutes. But this is just for the emulator trace. Now I can define the first and second params. Where I use my payment pub key hashes, the stake I defined, the deadlines. For nonce, for the first player, I just pick some arbitrary byte string, in this case, secret nonce, the NFT that I defined, and the choice is this first argument to the function C1. And for the second player, similar with choice C2. Then I just make the first player start. So H1 was his instance of the contract. So first player calls endpoint first with the FP, first params. Then I wait for 3 slots. So the first deadline was 5 slots. So the second player has time 5 slots to make his move. So waiting 3 slots should be fine. Now the second player calls endpoint 2 on his instance of the contract with his parameters. Then I give it another 10 slots so that this reveal deadline has also passed. And that's it. And now I can try it out in the REPL. So let's do this by hand, because if I call test, we'll just see many screens of log output and it will be difficult to see anything. So let's start with the case where both players choose 0. And in that case, the first player should win. And we see the first player is the one that in the end gets the NFT back. So this wallet here will be this first player. And we see first player, it started with 1,000 ADA and now has almost 1,100. So the discrepancy is due to transaction fees. And the second player lost a bit more than 100 ADA. So the 100 stake plus his transaction fees. Now let's try a case where the second player should win. So 0-1, for example. And we see the situation is mostly reversed. So this again is the first player, the one that gets the token back in the end. And the first player now has almost lost 100 ADA, and the first player has almost won 1. And the almost is due to this fact that I explained earlier, that the second player unfairly has to pay the deposit when handing back the state token. So as I said before, in a real implementation of this game, one should adjust that so that the second player doesn't have this unfair disadvantage. But it seems to work. So this was now the implementation without mentioning state machines, just with the means that we have already learned in previous lectures.